I'm right now in one of the marinas in Gothenburg, Sweden, and you may wonder what this has to do with chemistry, and even more so what it has to do with electrochemistry. But for the boat owners that have their boats here in the ocean, there is a really important connection here.
Electrochemistry is defined as the branch of chemistry that deals with the relations between electrical and chemical phenomena. Too technical? Well, basically, we rely on electrochemical reactions all the time. They are what keeps our phone going, unless you forgot to charge it, or our bike light working, what starts a car, and what alerts us if there is a fire. All these run on batteries, and inside a battery, there are chemical reactions that in turn supply us with energy to power all the things we need batteries for. Okay, so how does it work?
We know that atoms can take up or lose electrons and therefore become negatively or positively charged. This is what drives many chemical reactions, and in electrochemistry it is fundamental. But for an electrochemical reaction to occur, we also need a few other things. I am going to let Dr. Björn Wickman, researcher at Chalmers University of Technology, explain this.
To perform an electrochemical reaction, you need two electrodes, one anode and one cathode, and you need an electrolyte in between them, and you need a circuit that connects the anode and cathode. The role of the electrolyte is to let ions pass, transported through the electrolyte from one electrode to the other, while it has to block electrons from passing through the electrolyte. Instead, we force the electrons to go in the circuit, and then that can either generate electricity or consume electricity.
An electrolyte is usually a solution with free-moving ions that allows the substance to carry an electric charge. But there are a few things that need to be explained here. First, you may wonder why only the ions flow through the electrolyte and not the electrons. It has to do with the fact that the electrons choose the path of least resistance. The movement of electrons happens as they move from one element or molecule to another. The metals in the circuit can easily accept the extra electrons and therefore provides the least resistance for this movement. But for the reaction to even begin, there is one more important detail. The two electrodes, the anode and the cathode, cannot be the same metal. All metals are arranged in a series from highest to lowest based on their reactivity. This reactivity series basically indicates the different metals' ability to pull electrons to them or give off electrons to other elements. If you connect two different metals to each other and then put them in some kind of electrolyte, a fight for electrons will begin, and the element highest in the reactivity series is sure to lose. The metal at the losing electrode, called the anode, will then oxidize, meaning it will release electrons and dissolve into the electrolyte as positively charged ions. And at the opposite electrode, the cathode, positively charged ions in the electrolyte will instead be reduced, meaning they will pick up electrons. Since the electrons cannot move through the electrolyte, they will instead flow through the electric circuit, and just like Björn was saying, it is this movement of electrons that is electricity and the energy we get out of, for example, the battery. But we also have a second kind of electrochemical reaction that we need to mention.
If we instead add electric power, like when we put batteries on charge, we can kind of force the reaction to go in the opposite direction.
So by supplying electric power when charging batteries, we can force the reaction to run in reverse. But this doesn't work for all combinations of elements, which is why some batteries can only be used until they run out. Depending on what metal we have at the anode, the electrode where the electrons are being released, we can get different power outputs. Lithium and zinc are examples of two high-energy metals because they readily react and release electrons to form positively charged lithium and zinc ions. Lithium-ion batteries are examples of batteries that can be recharged over again. Alkaline, disposable batteries, which often have zinc-manganese electrodes, generally have a pretty long and consistent reaction time, but cannot be recharged. If the two electrodes had been made out of the same metal, we would never get this flow of electrons and our batteries would not work. Now we can put this knowledge in a real-life scenario. If we have two metals in contact and have some kind of liquid that allow the flow of ions through it, an electrochemical reaction can begin. This is extremely important to consider in construction, for example. Using the wrong metal combinations in the wrong scenario could have devastating results.
As boat owners with boats in the ocean, this is of course very important. We don't want the boat to just break down as soon as we put it in the water. But if you have a little bit of knowledge in chemistry and specifically electrochemistry, there are smart ways to get around this issue.
So if you introduce a less noble metal and you connect this to the exposed metal parts, this metal will be sacrificed and will oxidize instead.
By introducing a piece of metal, usually a block of zinc, that is sure to be more reactive than the part of the boat that we're trying to protect, we can create what is called a sacrificial anode, making our introduced and not so important metal part the anode of the electrochemical cell, which in turn makes the part of the boat that we're trying to protect the cathode. We then just keep adding more sacrificial anode as it is corroded away and our boat remains safe. Pretty smart, huh?
So I hope this helped explain electrochemistry a little bit better, and also why you should avoid as much as possible to drop things into the ocean, especially if they're made out of metal, they will get destroyed. All right, thanks everyone for watching. See you next time.